Okay, good morning. So today we'll talk about basic two errors that we face in numerical analysis and computation. There are the round of errors and the truncation errors. One of them arises because of the fact that we use finite memory and finite cells to store the values and to store information. And the second arises from the fact that we do not demand from the computer a full calculation for something. We truncate the calculation at some point because we know that accuracy we don't want it. So let's start with the round of errors. As you know, real numbers that you can do with them basically whatever you want, and especially the square root of 3 here, as you see, it is a symbolic way of assigning some number. So what is this number, the square root of 3? So you know that by mathematical analysis and calculus that you've learned, we have the nature of numbers which we assume to exist in our world using piano axioms. After that, you build a Q, the rational numbers. And after Q, using the Dedekind cuts, you build R. So what is this square root of 3? It is some number which is two sets A, B that are a partition of Q. I think you defined that in calculus. And after you build R, you build the addition in R and multiplication and everything. So the square root of 3, as we type it here, it is a symbol, only a symbol of some number that we all know what it is and how it is defined. But when we want to tell the computer what is the square root of 3, so we've learned also that this square root of 3 or real numbers, there is a bijection between decimal we call that decimal the infinite decimal representation of something and the real numbers when we don't account the 0.99999. And because of that bijection, we know that every number or real number, we can represent it as a decimal expansion, but an infinite decimal expansion. So we can approximate this square root of 3 up to any accuracy that we want in real life or in our mind or in abstract math. But on computer, we have given types of variables or given types of variables that we define, and we can assign the error of that based on that type. So why is it the memory finite? Is so clear to you? We use bits in computers. Why do we use bits although the real signals in computer are somehow continuous? Yes, they are analog signals of voltages and currents, but we use the 0-1 representation. Why do we use that? Why do we choose to store information by zeros and ones in computer, although we have continuous signal?
Because of engineering constraints.
which are
It depends something on off, and it's way harder to read continuously.
no, but I can represent any number I want by the amount of current or voltage that I have.
There can be intervals.
Exactly. So the zeros and ones are much less sensitive to errors, and because of error corrections, we use this way. So if the voltage or the current are above some cutoff or above some threshold, we call this one, and if they are below that, we call this zero. And we have a finite number of transistors or whatsoever, or digital circuits. So that's why that's why we have finite memory. And the known way of storing numbers is, for example, for integers, we can assign the integer to be positive or negative by the first bit, and the other bits will tell us in a binary way what is what its value is. And you have an algorithm to go from the decimal representation and the binary representation, yes, and vice versa. And the two these are integers and rational numbers or decimals. Let's call them that like that. Rational numbers or irrational numbers, but up to some point, we can represent them by floats or double floats. Yes, float and double float. And for the float, we use 32 bits. And for the double float, we use 64 bits. And the way we store them is by assigning one of these two bits for the sign, and we give the order of magnitude of the number 8 bits. And the rest are for what we call the 1 plus mantissa. Okay? So we have 1 bit for the sign. We have 8 bits for the what we call a order of magnitude. I will write here E minus B. And we have, this is the float. And we have 23 bits for what we call the mantissa. And the number is 1.m in binary representation to the exponent of A minus B. E is the exponent and B is the bias or the offset, and I will explain that. So we have here 1 bit, 8 bits, 23 bits. What is the number represented by this? It is minus 1 to the power of s times this. I will explain what is this, times this. Okay. So what is 1.m? The 1.m is 1 plus, we have here 23 digits or bits. So every one is M1, M2, M3. And every one I multiply it by 2 to the minus I. And I goes from 1 to 23. So this one is always on. We have some external bit, you can call it, that is always on. So this number, what do you know about it? It is, what's its value? It is between what and what? Huh?
1 and 2.
Yes, this is always between 1 and 2. It's valid. Okay. And what is this exponent? The exponent also in a binary, it's 8 bits, 8 binary bits, and its value is, and for example, EI to I goes from 0 to 7, and EI, for example, 7 minus I depends what you call E0 and what you call E1. So if I call the first one E0, then E1 until E7, so that's the formula for the value of E. And the bias is because of the fact that we want to represent also what? If this is the, so if there is no bias, if there is no minus b, what are the numbers that I can assign in this 32 bits? And also let's assume that not all of the EIs are 0, which means that the E has to be positive. So this means that not all of the EIs are 0. Okay. So which numbers can I assign if I use this way without minus b? What is the lowest number? Huh?
Larger than what?
All of them are larger than 1. So what is the biggest number? The biggest number is when all of these are 1, and all of what we put in the E also are 1. And this is the biggest number. But the lowest number is 1. And it's not good. I want also to go down, and I'm talking about the magnitude of the number. Yes, I have also negatives. But I want to assign also, or to be able to store also small numbers symmetrically as I can store large numbers. So I add this minus bias. You can say that the 8 bits in E can give me a number which is positive or negative, or equivalently, we can say this is the E, and always I subtract from this E the value of 127, so that I can run from minus 127, not minus because I have a minimum to be 1, so minus 126 until 127. Okay, so that's the E minus B. And this is for float. For double float, I have also 1 bit for the signal, and I have 11 bits for the exponent, and the bias is 1023, and I have how many bits for the mantissa? It's 1 and 11, 52. Okay. Any questions? Okay. So this is the way I store information or store numbers, and I assume that if I have an error in storing the number, only in storing the number, this error would arise where? you with me? If I have an error, if I want to store a number in 32 bits in this way, and there is an error in storing that number. This error arises only from the rounding because I'm using only 8 bits for the mantis. So where could this be error arise? What is this error?
So it's the
Okay, let's take it. Let's take the question to be easy. I have the number pi. You know, all of you know pi. And I ask you to write me the best approximation for pi only with 8 digits, 8 decimals. So 3.14 and stop here. Okay? So if you are good at math, and the only error that would arise here is only because you are using the finite digits, where this error could be?
only the
Only in the last digit, yes. Yes. And this error maximum, what would it be? 1 here, yes? 1. Okay? So for example, in this example, the error is smaller than 10 to the minus 8. And we say the bound of the error is 10 to the minus 8, and we take it as the error because we take the worst case when we deal with them. Okay. So always, also here, where would the error arise? Only in the last digit. What is the meaning of the last digit? What is its value? It is not 8 to the minus 8. It is 2 to the minus 8. Yes. The mantissa is 23, right? And so it is 2 to the minus 23. Okay, which is approximately with a meanings of 10 to the power of what is, yes. So it's 10 to the minus 7 up to the 10th digital 10th digit in the number, or after the point. And always I can use this argument, the 7th digit after the point, because I use this normalized way of writing the number. Yes. Originally, I have to say it is 10 to the minus 7 times the number, but always I represent the number as 1 point something. Okay, so it's always up to the 7th digit. That's my accuracy. Okay. And what about the relative error? I already talked about the relative error right now. The relative error of some number is the error of that number, epsilon round, which is, I have it here, okay. In some fields we use f exact minus f computed or computation, but I prefer the opposite. So let's take epsilon round to be f computation minus f exact, and this is as we said, this number. And what is the relative error, which is the error itself relative to the value of the exact number. So we won't store by mistake something wrong here, nor here. we can only be wrong only in the last digit of the mantissa. So the error divided by the number itself will give me the same sign, the same exponent, and I have only the 0.00001 in binary representation, and the mantissa, as we said, is between 1 and 2. Yes. So this error is only this number, which is 10 to the minus 7, divided by 1 or 1.5 or 2. So worst case, what is? 2 divided by 1. So we say also, we take this factor of 2, we don't care of it. So we say that the relative error is up to 10 to the minus 7. That's the relative error. And when we store, so now we know, when we store a number in float, we always have an error of 10 to the minus 7 of that number. So if the number is 1, the error, the absolute error is 10 to the minus 7. If the number that we want to store is 10 to the minus 4, what is the error of that number? The absolute error. 10 to the minus 11, yes. And if we want to store the number 1000, what is the absolute error of that number, of that storing? 10 to the 4 times 10 to the minus 7, it's 10 to the minus 3. So the mantissa, or the number of digits that are dedicated to that part, which is called mantissa, determine the relative error of this way of storing, and we can immediately know what is the absolute error when we know what is the value that we want to store. And we say 10 to the minus 7 for 32 bits, which use 23 for the mantissa, and when we use 52 for the mantissa and the 64 bits, which is the double float, that is 10 to the minus 16. So it's much better, of course. Any questions? Oh, so let's take this example. It's only an example. I think it is easy. Let's see. So we have here a number and its binary representation. We have the computer sees all these numbers in the bits. Yes, we have added these colors because we know that the first one is the sign, and after that we have the string of the exponent, and after that we have the string of the mantissa. And this is a 64. 64. This is a double float variable of type. And the exponent is like I wrote here, 2 to the 7. Okay, so that's for the float, and for the double float. And now I will write for the double float. We have here 10, here 10. We have here 52. So that's it. And we have here 1040. Eleven, 52. So the exponent is the red one, and we have 1 multiplied by 2 to the 10, and 0, 0, 0, 0 up to until I get this 1 and 1, which are 3. Yes, we remember that this number is 3. So the exponent is 127. And when we take minus the bias, we get 4. So this will be 2 to the 4th. Okay. And this is the mantissa, which is 1, 1, before all 1, 1 plus this mantissa, which is, so this is the 1, this is the 1 point m. So this is the 1 plus 1, half to the power of 1, and we have the 3rd and the 4th and the 5th. So we have 3, 4, 5 in exponents, and we have 6, 7, 8. So we have this 8. Okay, and the number is exactly this. Okay, so that number in the 64 bits is exactly this number. But this number, what could it be? What could it represent in real world? Yes, this is the stored number. So if I want to store this number, I want to store this number, so I can store it exactly. Okay. But also numbers near this, I will store them like this. Which numbers are they? Which numbers I will store them like this? So the same question I can ask you, which numbers I can store them as 2.5? You answer me every number, for example, between 2.45 up to 2.55, you store it in 2 digits like this. Yes? Okay. So in our binary representation, if this number is true up to the 52 or 52nd bit, so the error is up to that. So we add 1 bit and we subtract 1 bit. So that's when we add 1 bit, and that's when we subtract 1 bit. And this bit, its value is 10 to the or 2 to the minus 52. And the two numbers are these. Okay. So every number, every real number in the real world or in abstract mathematics that is between or that is in this range, we store it as the number that we say, and we have that error that we cannot run on. So if we want to store something below the minimum that we can store, this one is called underflow. So what is the smallest number that we can store other than 0? I want the smallest number in magnitude, but not 0.
2 to the minus 1024.
1022. Yes. Because we have here 2 to the 1. Okay. And minus 1023.
Oh, the exponent can be zeros.
No, the exponent I demand from it to be bigger than 0. Okay. Not all of them are 0. So this is also in float. It is which is in double float. in double flow, this is 10 to the minus 308, and the biggest number is also 10, and it's of order of magnitude 10 to the 308. And if I want to store a number which is smaller than this, I store it as 0. This is underflow, and in many times this underflow doesn't bother us. It's okay. But what bothers us is, but we have to know that we do this. Yes, we have to know that we're using very, very, very small numbers. It depends on the application. We have to know the problem that we deal with mathematically well. We have to know it well so that we can permit for ourselves to ignore these small numbers, but there are problems that we cannot ignore any small number. Okay. If we can ignore them, so it's okay for us, this underflow, but overflow is problematic. The program will say to us, there's an overflow, I cannot store what you demand from me to store, so I stop. Unless we take care of this in in the code itself. So again, this error of rounding is given by the machine. Yeah, if we want to store in 52 bits, that's the way. That's the error. We cannot round from that error. Okay. But the second error that we talk about is the truncation error. This error we can try to handle it with mathematical understanding. Okay, how to truncate things, when to stop, or when to cut something, and we also can manipulate it by using some special algorithms. So that's the essence of this course, to know how to deal with error that will propagate with your code or with your algorithm, and to know how to build a good algorithm so that the errors that arise, other than the round of error, so that they are small enough for our application or for our applications. It's good. And also the round of error, we cannot change it, but we can talk about how it propagates also. Okay, so but the truncation error, we can talk about it more and try to manage it or to handle it somehow. So what is the truncation error? The truncation error is an error that arises from a not full calculation of something. For example, not for example, if there are many calculations or computations that theoretically we have to do for them infinite steps, but we do finite steps. So this is not the same as the finite memory. We can have infinite memory and do finite steps, and we can have finite memory and do infinite steps. Okay, somehow. So this error arises from this fact, and the basic example for this is how to calculate, for example, the numbers, the sinus of some angle. Yes. So how your calculator do that? Yes, I think you know that. Okay, so I think that you know that the analog the digital circuits that we build use and or, and from that and or I can somehow build a digital circuit that adds numbers, and after that I can build subtraction, and after that I can build a big digital circuit that can multiply things. So okay, we can add, subtract, multiply, let's say divide, but how to calculate sinus something or cosine something. So it is also addition and multiplication, but up to some order. So what is this? This is the Taylor series of sine or cosine. So we tell the calculator only to calculate, for example, the first 10 elements in that series. And remember that the Taylor series is this, but to infinity. And if we want to approximate some function, which is, let's say, it's smooth and analytic in a point that it's surrounding, and let's say that that the error also goes to zero. That's what I meant when I said analytic. When we take n to infinity, the error goes to zero. So we can take more orders and be more accurate and accurate. But anyway, if we take up to the nth element, we know by Lagrange theorem, yes, you learned that in calculus, yes? We know by Lagrange that the error is this expression when psi is some number between x and x0, okay? And this is an exact equality, yes? But we want to say this is the approximation of f of x, and I have an error that I can bound. Okay. So, for example, you know this example, of course. If I want to do this around 0, x0 is 0. So x minus x0 is x, and I call it h. In this course, we will call h for these little steps that we will do in our numerical calculations. So I moved far from the 0 step, a little step, which is called h, and I want to calculate the sine of h. So by Taylor series, it is the infinite sum, and I can say it is h plus the third derivative of sine in some when I put its argument to be some number between 0 and h divided by this factorial and multiplied by h cubed. And this is true for every h, not only small h. Okay, this duality is true for every h. But if I put, for example, h equals 3, for example, or 10, let's say 10. Okay, so we say that the sine of 10 is 10 plus an error. This error is some number between -1 and 1, yes? So it is up to 1. And 10 to the, so this is 1000 divided by 6. So it doesn't mean anything. I tell you that this value is 10 plus minus 200. Okay, but if h is small, we have a meaning. If h is 0.1, we have a meaning. Yes, this number, this, what is the third derivative of sine? Yes. So this is between -1 and 1, and its magnitude is less than 1. And we can say that the error is bounded by h cubed divided by 6. Okay? So it has a meaning when h is small. And when we have something like this, we call it O of h, h cubed, and the meaning of this expression usually is that there is some number that I can, there is some constant c that I can write this down with. Okay, so it is efficient for us to say O of h cubed, because when we do the calculations, we will ask how much I will take h to be smaller. So it's much more interesting the power of h rather than this number. Okay. So we have two errors. So what is the total error of something? So we will assume here in this course that these two errors don't talk with each other. Okay, there is no coupling between them. They do not affect each other. They do not get one another to be bigger or small. Okay, so they propagate somehow without talking to each other. And for every variable in our memory, we have two errors: the truncation error and the roundover error. And when we let's say that you know why the truncation error is depending on a parameter h, but until now we don't know why the roundover depends on a parameter h. We will explain that. We will give an example. But what we want to say that we want the total error to be small. Okay, not necessarily the truncation error or the roundover. We want the total error. So there are two h optimals. Okay, one of them I define it. You have to be aware of this. In this course, we have two meanings of the word h optimal. So one of them is this, the optimal h that is good for our story or algorithm or whatsoever, is the h that takes this epsilon total to minimum. So it's the h that satisfies this equation. That's the h optimal. But we will have another meaning. The h optimal is the h that gives 0 for the epsilon, or the h that satisfies that the magnitude of epsilon truncation equals the magnitude of epsilon rounding. Okay. So let's take an example. We know that the derivative, the first derivative of function, we can write it like this, but computer cannot do this calculation because it cannot divide by a number which is very, 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 very small, close to zero. Okay. So we'll have here the overflow problem, but we want to calculate this derivative. So we remember our mathematical knowledge and we write that this derivative also equals the value of the function in x plus h minus the value of the function in x minus h divided by 2h minus this correction, where the sign now is between what and what? The psi here between which numbers? This is a number between what and what? In what range is it? Yes. Okay. So if you want, so we will ask the computer to calculate this. Okay, and that is the error. So let's take a break for that, and this break you can think or try to prove this argument. Okay? So think how to prove this. It's not hard. Okay, and let's take a break of 10 minutes. Okay. Okay, so that's the way we want to tell the computer to calculate the derivative, and we want to give it a small h for the error to be small enough, and we know that the error that's the proof of that. We know that the error goes like h squared. Goes like h squared, and its value is exactly that when the third derivative is is calculated in some point between x minus h and x plus h. But other than this error of truncation, that's the truncation error, yes? We have also the round off error, yes? Where is it? Where is it? It is in the values of f themselves, f of x plus h and f of x minus h. So we want from the computer to calculate this quantity f of x plus h minus f of x minus h divided by 2h and call it the derivative. But these values themselves also have the round of errors. So I write down these. And now the derivative that he thinks the derivative is this. Yes, that's the derivative that he calculates. So the error from the round errors is epsilon of the epsilon that was in f of x plus h minus the epsilon that was in f of x minus h divided by 2h. Okay, so we have two errors: the truncation error and the round off error. And you see, you may think that I may think, one may think that this error gets bigger when h is small. Yes, when h is small, it gets bigger. Okay, so that's a priori, and of course it will happen. But don't forget that we also don't know what is this epsilon. It is epsilon of f of x plus h, so it depends on h also. Okay, but we know that this epsilon is between 0 and let's say 10 to the minus 7. Also, this is between 0 to the 10. But we don't exactly know how they depend on h. Anyway, we somehow assume that they are somehow constants in a big range of trying many numbers, many small numbers of h's, and we think that there are ranges in these small numbers that this number goes bigger when h is okay, when h gets small. And the optimal h for us here is when these two errors are equal. That's the optimal for now, for example. And if we write this like this, we can say that the h optimal is this value. And do we know what is this? What this is? Can I calculate this now? I cannot calculate this because this h optimal, it is also this h optimal and also this h optimal. Okay, so and of course, if h is 0, this equation will be met. Yes, 0, h equals 0 satisfies this equation. Okay. And of course, it satisfies it because we don't have any error for h equals 0. Okay. Why don't we have any error? It equals 0 because this will be the same error. Okay. And although it's divided by h, so the third derivative will be some number. And anyway, in 0, we cannot calculate that thing because dividing by 0 is not, it's overflow. Okay. So equals 0 satisfies the equation, but we want another h to satisfy the equation and hope that the total error is 0. So what will we do? We say, for example, let's take h to be 10 to the minus 2. Okay. And then calculate this. Calculate the error in it's minus h and it's plus h, and we get what is the h optimum. But this h is not this. Maybe I will get 3 times or 1.7 multiplied by the 10 minus 2. So I correct again. Okay. And I correct again in hope that I will converge to some h optimum. In hope. I don't know if I will get there or not until now. Okay. Okay, so this is something that you should know, which is problematic. When we add two numbers, you remember that we save 8 digits for the order of magnitude. And we have 1 point n. Okay. Every number I represented as 1 point something and multiply it by 2 to an exponent. Okay, every number. So if I add two numbers that one of them is much larger than the other, I know that every one of them will be stored up to 10 to the minus 7 of it. Yes. So the first one number, 5 million, it will be stored, okay, 5 million, it's good. It will be stored up to the 10 to the minus 7. And this number will be stored up to the 10 minus 7 of it. But when we add these two numbers, the number that we will get is this, and this number will be stored up to the 10 to the minus 7 of it. So it will be stored as this. Okay? So we lost 10% of the small number, which is 5.55. Okay, it is from the total number, it is 10 to the minus 7. Okay, that's okay. But in this addition, we lost 10% of the small number. So when we add two numbers, one of them is much smaller than the other, we lose the information about the small number. Okay, so we have to be aware of that, and we have to know how to manage this if we want to manage it. Okay. And this is an example of trying to optimize the total error. Again, the examples here are so simple. So we want to evaluate this function for small numbers. Okay. And we know that for x equals 0, this function goes to 1. Yes, you can use L'Hopital. So we want to tell the computer that this function, if x equals 0, so it is 1, and else you can compute this value. But we know that for small values of x, it cannot do that because of the overflow problem. Okay, it cannot divide by any small number. So we try to change this condition, and we tell the computer if x is smaller than some very small number, which is, for example, 10 to the minus 5. And now, after we wrote this, and here the condition is x is smaller than 10 to the minus 5, we want to ask what are the errors in this function. We wanted this function, and we told the computer to calculate another function, which is an approximation of this function. And now we want to know what are the errors, or what is the error. And we will focus on the borderline case around this 10 to the minus 5. Okay, so for numbers that are close to the 10 to the minus 5 but are smaller, we assign the value to be 1. So which error, and 1, if we want the computer to store 1, what is the error in storing 1? Yes. So I wrote here 0, but it's what we say. It's 10 to the minus 7. That's the rounding error. And what's the truncation? If I told the computer to assign it as 1, or to save it, or to store it as 1, this is a truncation because the function is 1 plus something. Okay? That's the function. F of x, you can take the Taylor expansion, and we know that this something goes like x to the x divided the half of x in its bound. Okay, the bound of it is the half of x. And then the truncation error is 10 to the minus 5 divided by 2, or 10 to the minus 5. Okay, we take the order of magnitudes. Okay, so that's for numbers below that.
Why 5 and not 7?
Because
we chose
a priori, you're true. I can take 6, okay, for example. But a priori, I somehow don't know what will be here. Okay, so maybe it's a big number, but it's small. Okay, and above 10 to the minus 5, we somehow assume that the computer knows what is the exponent exactly, but when it uses finite cells, it rounds it. So there's no truncation error, but there is a rounding error, and the rounding error is crucial here. But what do I mean by crucial? It's bigger than the 10 to the minus 7. Why? Because it is 10 to the minus 7, okay, in the e to the x, okay? So the e to the x, for example, e to the 10 to minus 5 equals this number, and it might store it with an error of 10 to the minus 7, so it might store it like this, okay? So that's the e to the x. But now we take minus 1 and then divide by x. So because of that minus 1, you see, take minus 1 from this, take minus 1 from this. Now these two numbers are differed by 1%, not 10 to the 7, to the minus 7, okay? So the answer of f will be, the true answer of f, let's call it, will be this. But when we take the error of rounding, it will be like this. And the error between these two numbers is 0.01, and the relative error is 0.001 divided by this one, which is 1%. So it's a big relative error. And if we go to the double float type of storing, it will be better. So we will have a relative error of 10 to the minus 10 in both errors. Okay. Okay, now that's something that is also basic and simple. We want to know how the error propagates. Until now, we have done only one calculation. Yeah, only one. For example, in the previous example, there was the rounding and then one calculation, which is the -1, and dividing. Okay, 2, and then we could know what happened. So in our code, there will be many calculations, and the error will somehow change, and somehow we will accumulate errors and gather errors, and we hope that these errors will be somehow enough small. And let's ask what we have if what will happen if we have two numbers with, or two variables with two errors, and we want to add these variables. Okay, so the error of the result is the sum of the errors. Okay, and the relative error is the sum of the errors divided by the sum of the numbers. But this will be problematic when p equals, or p is near the minus q. Okay, so if we have an error in p and we have an error in q, but the p is minus q somehow, not exactly, then this will be close to 0, and this will be an error, but this is close to 0. Okay, so then when we have a big relative, so when we add two numbers, or when we subtract positive numbers, we have some problem when these numbers are too close to each other. Yes, then then the error of that subtraction will be relatively larger, or relatively large to the real number, to the actual number that we we are seeking, let's say. And what happens when we multiply numbers? So we take not the multiplication of the errors, no. We take also the multiplication, the cross multiplication between the error, the sum of that. Okay. And if these errors are small, so this is enough for us to say that it is the error. And we can divide by p times q and ask what happens with the relative error. So the relative error of the multiplication is the sum of the relative errors. Yes. So for addition, the relative error is the sum of the errors divided by the values, the value of the sum. And in multiplication, the relative error of the product is the sum of the relative errors. Okay. And again, we hope that our algorithm to be stable, not stable. Okay, we if they are stable, it's fantastic. Okay, but usually we don't have stable algorithms, but they grow. The error grows with the number of steps. But we can ask how does it grow? So if the error goes linearly with the number of steps, it's good enough for us. But if it goes exponentially, it's very, very bad. Okay. If we add steps, the error grows exponentially, it's very bad for us, and then it will be much larger than the values that we want or we seek. And if it goes exponentially, but it decreases, yes, it is an exponent of a small number, smaller than 1. So then we will say then that the algorithm is stable, yes. But usually we don't have stable algorithms. We have algorithms with a growing error, accumulating error. But the question is, how can we restrict this error to grow slowly? Okay, so now, okay, so now let's try to solve this equation. If we want to solve this equation, it's this is for your homework. Okay, this note is for your homework. If we want to know the roots of this quadratic formula or equation, we know that the roots are these. Okay, so this is the first, this is this. And we know how to calculate the roots. If we call the first A and B and C, A equals 1, B equals minus 1.7867, and C equals 2.0543. Okay, so we know that x12 equals to this. That's how we find the two roots. But when we calculate b squared, you see what is b? Minus 4ac. So we subtract a small number from a big number, which is the b squared. So we lose information from the small number, and the square root of this is very close to what? It is very close to what? The square root of b squared minus 4ac to b itself. So we will have minus b plus minus b. And the first root, which is minus b divided by 2a, is okay, is good enough for me. But the second root, which is minus b plus somehow b, if b is positive, here b is negative, so the opposite. But if b is positive, the second one will be close to 0, and the error will be larger than usual. Let's say that larger than usual. So can I modify this, or can I make some trick to have a smaller error? The answer is yes. Okay. So I will get there. I will get an answer. Not that I will not get an answer. Okay. So let's see. So here we get an answer. Okay. Let's see here. So I define A equals 1, B equals, C equals, and I know what are the true values. See, these are the true values. And I write x1 equals, x2 equals, it must be divided by 2a, but the a is 1, so it's good. And then I print x1 and x2, and you see x1 and x2, and let's look at x2. X2 is deferred from the true value of x2 by we have a change in the 8th digit after the point, so it's up to, the error is up to 10 to the minus 8. Okay, that's the error, 10 to the minus 8. So can I have smaller error? The answer is yes. I simply run away from this calculation for the second root. Okay, for the second root, I don't do this calculation because it's not a good calculation. So I have other ways to calculate roots of the quadratic equation. For example, when you find the first, that you know that that its error is very small, you can find the second by C divided by A divided by this. So it's called the Vieta formula. Yes, you remember that from high school? No? Okay, so it's written here also. So when we have this quadratic equation, then we know that the sum of the roots has to be minus b divided by a, and the multiplication of the roots must be c divided by a. You know that this, no? Yes, no? No? It's from high school.
We didn't learn it specifically, but it makes a lot of sense.
Okay. Okay. That's it. Nothing more than that. So so we can find, it depends now on the sign of b, which root is better. So if the b is negative, we calculate this this root, and the second root, we simply take the first root and c divided by a is 1. And when we do this, when we somehow don't do that b squared minus 4ac, we do another, and then add it to a close number, and they are close to 0 now. We do another calculation, which is this. It is better. It will be now up to 10 to the minus 16 or 15. If we take this. Okay, so we have a much smaller error. Okay, so here is an example how we try to manage errors when we know the mathematical background. Yes. So always we have to use our mathematical knowledge in order to build good algorithms to have small errors. Oh, this is a very simple example. And in your homework, you will have some of these, and I will just tell you that you can seek this in Wikipedia, not more not more than this. So finite difference equations are equations like these, and there is a simple way to solve them. It is based on a guess. You guess something and you solve the equation. All of these equations have the same solutions, but we want for you to see here in this exercise how the errors propagate when we try to solve this numerically. So you have in your homework 2 theoretical exercises, questions, and a third problematic one. And I say here recall, but it's not recall, so you can find it in Google. It's only guessing and then finding the solution. Also, if have you learned the Fourier transform? Yes. So there is also the Z transform. You know it, the discrete Fourier transform. Okay, so we can also solve these equations. These are simple equations, but finite difference equations we can solve them also by using this transform, and then it will be a simple equation, and then we will have to do the reverse or inverse Z transform to get the solution in terms of time, and you can say it's a sequence that you have to know what is closed form. Okay, so you have to guess something and continue. So that's it for today. I see that the recitations are short somehow. Maybe the next one I will add another exercise, and maybe I'm too fast, maybe no, I don't know. Any questions? Okay, so that's it for today. See you